Wow, this one was substantially harder than the first one. Unique binary trees level 2 is much harder than the second level. If you haven't seen first level, please check it out. This one is a lot harder. Okay, basically what you have now is you are given an n. An n means you get a list of numbers 1 through n. And what you have to return is a vector of tree pointers, where each pointer is pointing to a tree, such that all of the trees are covered in the vector. So for example, what you'd push back is you'd somehow make a tree like that looks like this, push back 1, make a tree looks like this, push back 3, make a tree that looks like that, push back pointer to 3, this pointer to 3, then that, push back pointer to 2, and on and on. Wow. Okay. So first you're gonna push back a vector of tree node pointers. That's the first thing we gotta keep in mind. Okay. Let's go to the board. What color should we use today? I am feeling, should we go orange? Yeah. Fiery orange or yellow orange? What about just, yeah, yellow's too hard to get. Okay. That's like a brick orange. I want a fiery there. Well, that's also kind of looks like a brick. It's okay. Beautiful. Okay. Let's say we have 10 as our input. So that means we're going to have 1, 2. This is our list of numbers that we have to work with. And what we have to do is we have to come up with all of the combinations of trees and then put the roots in each one of them. Okay, so as you probably already know, each with this being the root, there could be a lot of trees. With this being the root, there could be a lot of trees. So there's going to be way more than 10 trees. And in the last video, we got the number of how many trees there were. Okay, so one idea with the last video of how to do these problems is you go through and make each one of them a head. So like, let's say we made 5 ahead. So that means we have 1, 2, 3, 4 on this side and 6, 7, 8, 9, 10 on that side. And what you want to do is, and then, so that's how that works. So what I want to do for this one is I want to make it recursive. Recursive in the fact that we go through each one of these and make them all the heads. And then what I want to do, this is the tricky part, is I'm going to send this off to my array, to my function again, and I'm hoping this is a recursive leap of faith, that this is going to give me a vector of tree nodes that goes through every single combination of these trees. So I want it to go 2, 3, 4, and 1, 3, 2, 4, and all of the many combinations that. And I want this vector that it returns to give me pointers to each one of these roots for all the combinations. And then what I want to do, and I want to do the same thing to this side of it. And then what I want to do is so then popping back to this level, where I'm going through all of these, making all of these roots, then I want this iteration to make 5's left guy point point to one of these. So for example, here. So it's kind of like this is pointing here. So 5's left is going to point to this vector at index I or something. And then I want to push this new root, actually, that's all I'm pushing, the root, into the resulting vector. I want to push this into the resulting vector because now it includes 5 plus one combination of here. Then I want to do 5 right side, actually, gets one of the combinations here. So vec2 at 0. And then once I have a left and right side, I'm going to push 5, the pointer 5, into the original resulting vector of tree nodes, because it's kind of like we're making all these subtrees here. So like 5's up here, then 1, 2, 3, 4. We're making a subtree that looks like that or that or that, and we have all the combinations. And then we do the same thing with 6, 7, 8, 9, 10. We make all the combinations here. Okay? And that's kind of, those are our recursive leaps of faith. We're hoping that these do that job. Then what we're going to do is we're going to build upon each one of these pointers in the vector by putting a 5 before it, and then taking a combination of one of these and one of these, and going through all the combinations. So in total, the amount of combinations, if you listen to the last video, is going to be however many combinations, like the vector size here times the vector size over here. That's how many combinations we're going to get. Okay? So let's start off by writing some stuff. So what we could pass to our helper. Also, I kind of realized that almost always you want to be returning in your helper function the same thing that you are returning in your regular function. And what I'm going to pass through is, since these are all contiguous numbers, like numbers that go right in order, I can just pass a range. So if I have int start and int end, I could return helper 1 to n inclusively. And that will hopefully give me a vector of all the combinations of numbers using numbers 1 through n. And it's going to give me a vector of pointers of roots, where each root is kind of another tree. Okay, so let's see what we want here. So first, what we want to do is we want to go through all the numbers here. So actually start, not 0. We got to be careful because, yeah. And then less than or equal to the last one, and then I plus plus plus. Okay, so this is rotating all of the heads, like here. Like first, you're the head, you're the head, you're the head. Then what we want to do is, well, actually first we should always make our thing that we're returning first, really. So let's just call this, I don't know, v. No. Yeah, v is fine. Okay, so then what we're going to do is we are going to take the vectors, then like let's say we're at a random iteration like 5 again. Sorry, that was bad. So we're at 5 again. What we want is to do this process here, where we get the vector of all the things on the left side and all the things on the right side first. So what we can do is we could do vector tree node left gets helper, and the start, we should leave it at the start that we had, because for example, if we're going through this iteration here and we got to 5, what do we want to pass here? We want to pass our current start, right? Whatever our start was up here when we started the function. And we want to go until this 4, which is going to be I minus 1. So I minus 1, and then similarly, dang it, I minus 1. Okay, and then similarly, we're going to want vector tree node pointer to the right side equaling helper. And then we're going to start at I plus 1 all the way to the end. Okay, so now that we have these two vectors, what we're going to be doing is putting 5 in front of all the combinations of all of those, and then for each one of those, we're going to put this in, we're going to put it in our v, our resultant vector. So for int I equals, no, can't use I, j equals 0, j is less than, actually we could honestly just do a range for loop. So this is going to be tree node pointer L, and that's going to get, so I want it to go through all of the left ones, and then for tree node pointer R going through all of the right things. And so then I'm going to make a tree node with our integer I. Oh, I should call it root. We could call it root. And then we do root left gets L, and root right gets R. So this is just for one combination. You know, notice how we're going through every combination of left and right values. And then after we have both of those in there, then we can push back all of those combinations to V. So I can push back that root. Remember, we are pushing tree node pointers back there. So, okay, so we did that. So that should push back all of those for that iteration. And then where do we want to return? Well, we want to return after we went through all of these, right? Back to the first iteration. We will return after we push back all the combinations of here and here and here and all of those too. So let's return v here. Okay, so if you think we are done, you are wrong, because we still have to deal with base cases, right? When does this, well, yeah, we have to deal with base cases. It will automatically end, right? Because eventually start is not going to be less than or equal to end. So when that happens, let's think about what we should be doing here. So if start is greater than end, so what that means, so let's get to an example where that happens. So actually, even in our first time, when we are looking at 1, right, let's go down and analyze that more. So 1 is the head, and here we got nothing going on the left side, and on the right side we got 2, 3, 4, 5, and we'll ignore this side for now, okay? That side we know how to do. But what about this side where there's nothing here? So if 1 is the head, the left side is actually, should be null probably. It should be pointing to null. So let's think about what is going in the left side. So here we have left side gets helper start to I minus 1. So start is going to be 1. So this is like what left side, the vector that's going to be going to it. It's going to get 1, and then it's going to I minus 1. So I is 1 right now, so it's 0. So our start is 1 and our end is 0. So what we can do is, so if our start is bigger than our where we're going to, and this definitely can happen. I mean, in this instance, it definitely could happen when during the first iteration. Actually, that's when it happens all the time, because I starts off at start, and we are going from start to I minus 1. No, like, we do want to go start to I minus 1. That's not really an error. So we do want to keep it there. But if it's the case that there's nothing really, there's nothing to the left of the I, which is what this is telling us, then what we could do is we can return a vector with null in it. And actually, we can do that here with like nothing in it. So yeah, I think if we just return v here, that's fine, because v is going to have nothing. And then so if left gets nothing in it, well, then tree node is going to have nothing to get out of it. So maybe we should just return null. Okay. And I think we could actually return null, and that'll return a vector with just null. I think I saw that somewhere. I'm not 100% sure about that. I might have to push back null. Well, it's pointers to tree nodes. So I'm pushing back a null pointer. Yeah. Okay, and that should be the only edge case that we should have to deal with. Oh yeah, one more. If n is 0, let's see. If n is 0, then it's automatically going to be in this thing, and we're just returning null. Is that what we want? What do we want to return? We want to return. Do we want to return? So if there's just 0, we do want to return a vector with that. Okay. I'm not, yeah, okay, they didn't like that. Okay. Include, could not convert 0, 1 to that. Okay, what about lowercase null? Sorry for these technical difficulties. Okay, let's do v dot push back null, and then return v here. Okay, is it? I thought it was capital like that. Root left. Nice. Oh wait, yeah, this should be a pointer to a tree node, and that should get new tree node. Yeah, that should be the syntax. My bad. Okay, that does look good, and I want to see what happens when I put in 0, if I get it right. No, so it's expecting. Okay. What if I return here a null pointer? Yeah, okay, that I might be able to return. No. Okay. So what I'm going to do is apparently that this is not I need to literally return nothing, so I have to have this case here. If n equals 0, return just got to return this, almost this. So if you want to return something empty, you could just do vector that and then these parentheses, like making a function kind of, and that does it. Okay, so I'm pretty confident in this. Let's see how I do. I have done this before. Okay, great. Yeah, so let me recap before I end this video. So basically what we're doing is we are going through, this is basically rotating which guy is head. And all we need is a start and end. We don't need a vector being passed through this recursive function. We just need a start and end. And that is because our list of numbers is continuous from 1 to n. So our subsection of an array, maybe in a different problem, can be substituted by just having 2 bounds because we're just going through each number in between them. Okay, so this line again is rotating which thing number is the root. Then what we do is we do this recursive leap of faith where we get the left. We get the, so remember with recursive stuff, you have to work with what you're returning, okay? So we are returning a vector of tree nodes. Okay, that's fine. So with my root here, let's just say, let's go back to the 5 again. With my root 5, how could I compute all of the combinations of trees with 5 as a root? Well, let's see what information you could have. You can get, I'm telling you, this is the recursive leap of faith, that I could get you a vector of tree nodes to any, I could get you a vector of tree nodes from, if you give me a start to end, that represent all the combinations of those trees. So I'm going to say fine. How about you give me a vector of tree nodes 1 through 4. So you give me all the combination of those trees using numbers 1 through 4. And while you're at it, why don't you give me all the combinations 6 through 10? Okay, so that is very useful. Remember, we got to use what we got. We got to use what we're returning. That's very useful because now, in order to make my 5 my root, and all the combinations that go with it, what I could do is I could insert my 5, which is going to be here, and get one combination of each of them. Until I go through all the combinations of both of them. I have 2 for loops. The 2 for loops are going through and making all the combinations of everything, right? Because while the left one is just stuck on maybe this one, I go through all the combinations of 6, 7, 8, 9, 10. Whoops, now I go, or not whoops, now it's like more like click, click to the next iteration of left. Now I have this one. Go through all of these again. And that's what this double for loop is doing. So I really am getting all the combinations of 5, and I'm pushing that back to this V root, to this V. Okay? And V is also storing, it already got all of these, and all the combinations with 1 is the root, 2 is the root, 3 is the root, 4 is the root. Okay? And this does, and then after you have to think to yourself, does it work? Because what's going to happen is after we get 5, and then 1, 2, 3, 4, 6, 7, 8, 9, 10, this side is going to split up too. It's going to make this the head, 6, 7, 8, 9, 10. It's going to start with 6 being the head, then 7 being the head. And then let's look at what if 8's the head, then 8, we got 6, 7, we got 9, 10. Then it's going to split up here again. We got 9 as a head and 10 as a head. let's make 9 the head. So then we got 10 here, right? And then maybe we, like, using these, we got 10 and we got 10, 9. So basically this is going to return a vector that looks like this with pointers pointing to these two trees. Okay? And then 8 is going to basically insert itself in front of both of them. And then using these, it's going to go through all the combinations of these two. So we got 6, 7, but then we also got 7, 6, and so on. Okay? So I also have heard about some memoization here, some dynamic programming, because we are computing a lot of these many times. We are computing 6, 7, 8, 9, 10 many times, and we're computing a lot of these many times. So there might be faster solutions out there. I'm only at the 50th percentile, but this concept with recursive thinking like this was hard to think of, and I wanted to explain it to you guys. Okay, so I hope you learned something. I hope you relaxed during this video. Maybe I'll give the video on the memoization version. If you guys want it, just leave a comment below. But until then, I'll see you guys next time.